and you still prefer research group. So this is a shared work with my colleagues from University and based on that. So I assume most of you are familiar with the term FFT. It's one of the most efficient and most important algorithms method. But I think you are not that familiar with zk and Halo2, so we'll give you a brief explanation of what they are. So zero-knowledge proof is a proof which allows one party, to the prover, to prove to another party, to the verifier, that some statement is true without revealing any additional information. If we take more mathematically, the prover knows some secret x at which this function f equals to y, with one value at which point x is equal to y. So it has many use cases, from private blockchains, zk rollups, identity verification, and so on. And it is zero-knowledge proof. It has three most important properties: the prover time, proof size, and verification time. So the prover time is usually, if let's say the difficulty of a function is on, then the prover time is usually quasi-linear. So it could be on or on log n. And proof size and verification time are either constant or they are logarithmic. In case of our zkFFT protocol, we try to get a practical verifier with very fast prover and very small proof size. One more thing which is very commonly used in many zero-knowledge systems is the Patterson commitment scheme. So what is a commitment scheme? It's a scheme which allows you to commit to some values, and later on, it's similar to like writing something down and putting it in an envelope and then sealing it. So while it's in the envelope, no one can see what is there, and when it's opened, we can be sure that our values were not modified. So in case of Patterson commitment scheme, we can commit to the values, and this CA will be commitment to the values A, and it's based on the discrete logarithm assumption. So having g to the power of A, you can't get A, as long as the discrete logarithm is hard. So the motivation of our paper came from another paper called Calc trees. I don't want to go into details of how Calc trees works, but it's important that Calc trees are a very efficient zero-knowledge proof system for set membership proofs. Which is basically you have some committed set of values, and you can prove that you are a member of this set. So where it can be used in private blockchains, when you have, let's say, a set of transactions or a set of addresses, and you want to prove that you are one of them. And these Calc trees are based on a cryptographic protocol called bullet proofs, which on its own is based on other cryptographic protocol called inner product arguments, IPAs for short. And at the moment, the most efficient IPA-based protocol is called Halo2. So we decided, okay, if there is Calc trees with bullet proofs, then maybe we can make them even more efficient by using this system called Halo2. So how Halo2 works, it takes all our values and puts them into some sort of matrix. So it can be different part of data, but also it will include the commitment to these values. Yeah, because as we said, the idea of membership proof is you have some committed set of values, and you want to prove that you are a member in this set. So the Halo2 system will take these values, it will interpolate them, and commit to the coefficients of these polynomials, and then make a proof using IPA. So as you can see, we will have two committed vectors after using Halo2. We have two committed vectors. The first one was our pre-committed vector, which is a vector to the values of this polynomial, and the second one is the vector we get from Halo2. This is the commitment to the coefficients of the polynomial. By the way, if I'm moving too fast or too slow, I think I can mention, or maybe I don't know, the speed is okay. So basically, we get two committed vectors. And from now on, I think you can understand where this name zkFFT comes from. If original FFT allows you to get coefficients from the values and values from the coefficients, then the idea behind zkFFT is to show that one committed vector is an FFT of another committed vector. Yeah, because as I just showed, we'll have one pre-committed vector, it is the committed set of values, and the next vector which we get from Halo2. You may ask why this was not a problem in original bullet proofs, in original Calc trees, and why it wasn't always solved there, but the thing is, culture is based on bullet proofs, and I don't want to go into details, but bullet proofs can be very easily extended to support extra vector commitments, which is not the case with Halo2. And again, bullet proofs is not a problem, you can easily extend them. So now that the problem is fully stated, we can try to understand how we can solve this problem. As I just mentioned, the Halo2 uses IK, so let's see what IK does. IK allows you to show that if you have two committed vectors, vector A and vector B, you can show that U is the commitment to their inner product. So J is a commitment to A, HB is a commitment to B, and U is commitment to their inner product. And this alpha is just randomness. And if I rephrase FFT a little bit, we can say that FFT is just an inner product of the coefficients of a polynomial and its roots of unity. Because if I take coefficients of a polynomial and do an inner product with their corresponding roots of unity, let's say in case of one it will be W, W squared, W cubed, W four, and so on, I will get just V1, and the same way I can get V2, V3, and so on. So it looks like that, okay, actually, I can just make an IK proof about our FFT. But the thing is, if we try to make an IK proof, we will be forced to do n IK proofs, because there is not just one value V, there are n values of V. And as the size of each IK proof is logarithmic, this will mean that our whole protocol's proof size will be O(n) log n. And as I just mentioned, usually you want to have a proof size which is at most like log n or polylog n, but never something comparable to O(n) log n. So here we decided to create a new argument called modified product arguments, which instead of just original inner product arguments, allows you to prove something about two vectors, but k plus 1 vectors. So you have one vector A and k vectors B1 to Bk. They are all committed. And we can prove that all of them, all U's are a commitment to these inner product arguments of A and corresponding bits. If you look closer to this, you can actually say that this is not that big of an improvement compared to just NIKs, because, yeah, okay, we managed to maybe, we can like run all these IK proofs simultaneously in one modified IK proof, but still we will have to use some values of these P's inside the proof. So this means that, okay, we make the proof size smaller, but not drastically smaller. This will be again comparable to O(n) or maybe O(n) log n. But the interesting thing about our proof is that what are B's in our case? In our case, A is, as you know, the commitment to the values, commitment to the coefficients. And B's in our case are just these vectors or roots of unity. So this means that if A and corresponding B's are private and they must be committed, actually the roots of unity are not private, they are public. So this means that they are also known to the verifier. And if they are also known to the verifier, we can remove them from the proof. We can just let the verifier on their own compute these values of B and check that the proof is correct, even without getting anything about B's, because all the B's are just vectors or roots of unity, and they are publicly known to everyone. So this means that our zkFFT protocol will be far more simple. And it will be just a commitment to our coefficients, and it will be multiplied with commitment to the inner products, where A is our coefficient and each B is our corresponding roots of unity. So because of doing this, we can see our benchmarks and try to understand how efficient actually zkFFT proof is. As zkFFT is something rather new, and there is nothing like zkFFT or nothing like modified inner product arguments, we decided to compare it by just doing native multi-scalar multiplications. So like, let's say instead of doing zkFFT proof, what if we just did multi-scalar multiplications and try to make the same proof. And as you can see, and as I mentioned at the beginning of my talk, our prover is extremely fast. It's approximately 5 times faster than just naive MSM operations. And the proof size is again 5 to 6 times smaller compared to naive MSM. But of course, there is the downside, and downside is that the verifier time is around 3 times worse compared to just making an item and some computations. The reason for that is that, as I mentioned, here we have to make all the computations about bits, which are vector of roots of unity, and the verifier have to do on their own because we decided to remove them from the proof. So we made very small proofs, but a little bit slower verifier. In real world use case, this pointed a bigger problem. In paper, we show that you can aggregate many proofs and make also a large verification of many proofs. So if, let's say, in real world use case, you don't have just one vector, but you rather have 10 vectors, this verification time will still be quite okay because you do batch into 10 proofs, and batch verification of 10 proofs is not that bigger compared to just verification of one proof. So to give you some idea on what our paper does, it makes like 3 statements. First, we just extended the Halo2 to support vector commitments. It may be another problem. It is not necessarily the hardware problem. It can be used in maybe other possible problems. Second is we show that hey, it's indeed possible to make cartridges with Halo2, so it's indeed possible to make more efficient, even more efficient than just original cartridges, actually membership and non-membership proofs. And also this extension is not basically only Halo2. You can take some other protocols which are similar, which are using IPAs, but maybe a bit different articulation, and you can still try to apply Halo2. We didn't do it in the paper, but if you have some specific protocol, you may try to extend zkFFT. And the third thing is that zkFFT standalone is just a novel zero construction, and it can be used maybe in very different areas because, as you know, FFT is used everywhere, from like signal processing to zero knowledge to any other field of science. So basically that was it. Thank you. I obviously that was not too fast or too slow, so I will be happy to answer your questions.
Thanks, Hayk. Any questions?